All right. Well, I'll get started here. Let me hand out the attendance sheet before I forget. It's been a minute since I handed this one out. Don't worry, it still works. Let's see here. What's today's date? Man. Yowzers. Here you go.
Thank you.
I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students, this class. Just ask you to bless our work today. Help us to glorify what we do and just to make the most of this week, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I think I owe you a statement and proof of the divergence theorem at this point. So let's get into it. So the divergence theorem says that the integral of the divergence over a closed simple solid is equal to the flux through the boundary of said solid. So the divergence theorem says the following, if you'll allow me to just forego the niceties in terms of, the, what's the words? The fine print, if you will. So the boundary of a simple solid E of vector field, the flux through that is equal to the triple integral of the divergence of the vector field throughout the volume. So that's the divergence theorem. And what I'd like to do is just to try to describe a pretty simple proof of why that's true based on things we've already done. And so what I'm going to do is, so here's a proof sketch, which I mean it's a proof which is slightly sketchy, so, but mostly unsketchy. We're going to let F equals to PQR. All right. And what I'm going to do is I'm going to consider the region to be something like this. All right, so like a little, what do you want to call it, pillbox or a little cylinder, all right? And now what I want to do is try to count the number of field lines that are coming out of this, all right? So really there are, let's see here, a couple different things to talk about. Let's say that this bottom is at Z, and this up here, we'll call this Z naught. This one's at, this up here is at Z naught plus delta Z, right? And so like you've got ds vector here, and then down there your ds vector points down like that. So in both of these cases you can just put like z hat, right? Z hat dx dy will serve as the surface area element, and down here like minus z hat dx dy, okay? Does that make sense? So I'm assuming that the top and the bottom of the cylinder are horizontal in the sense that they're like, you know, all of a sudden we got double straws. It's very exciting. We've only had single straws up to this point. All of a sudden today we got double straws. I feel very important. I finally made it. But it's kind of about to poke me in the eye, so I'm going to throw it out. Oh well. Sorry. As you know, I'm easily distracted. So there's a surface area element above and below. And the surface area element on the side, you know, it's more exciting, right? So here's ds. I'll just picture it. So let me point out some things. This distance here is delta z, right? And so if I want to count the number of field lines that go through the side, in other words, the flux through the side, the curved side, all right, that should be something like delta z times like the flux through a given, circle. Now, I say that through any circle I want in there, because essentially if delta z is what? See, if delta z is small, then the number of field lines that go through that circle is the same as the number that go through each one. So if I want like the number of field lines total, I just take that times that. Anyway, my point here is that this is just delta z, and then the integral of, let's see here, f dot n hat ds. Going back to how we defined like the number of field lines through a curve. So basically, if I take that times delta z, that should give me the number of field lines through the curved solid. But of course, we had a method to calculate that, right? We worked out that Green's theorem told us that that was in fact the integral of partial p partial x plus partial q partial y dA. All right. And that would be over like this region R, all right? Of course, you could take it to be like just R at the base if you wanted. Maybe I should do that. Just think of it down here for the sake of specificity. Let's take that R to be down here. Again, as long as the delta z is small, it shouldn't really matter where we calculate that, because it shouldn't be much different whether I use z naught or z naught plus delta z. Like that integral should be essentially the same, all right? And let me point out that you could switch this up, right? That integral, we could just as well write as the integral, the triple integral, over the entire thing, which let's call it E, right? Of partial p partial x plus partial q partial y, dx dy dz. Do you see why I can do that? Does that make sense to you? It's like delta z we can rewrite as an integral of dz over the appropriate bounds. So this is equal to that, just changing the delta z to an integral over dz. And using the fact that we're assuming that delta z is small enough, so essentially these area integrals are all the same at each z. So anyway, so there's that. Again, this is a slightly sketchy proof, but it's the spirit of the thing. And then, okay, so that's the flux that goes out. That calculates the flux that goes out through the sides, right? How about the top and the bottom? What's the number of field lines through the top? So when you take f dot, when you take f dot ds top, what do you get? You get, what do you get? We get f, we get r, right, of x comma y comma z naught plus delta z. All right? So we'd have exactly, r of x comma y comma z naught plus delta z times what? Well, I guess I need to integrate that over the dx dy. And that would be over, let's say, R, I don't have a name for it, but this R up here. I guess I should come up with a different name. Oh well, it's too late. I've already used R for it. I'm going to call it R again here. Now the number of field lines through the bottom, what's that? Through the base. Notice that the field, vector field dot the base S, right, is what? Minus R. So you can z hat, when you take z hat dot ds, the only part of F which is actually piercing the surface is the part that's the z component, right? It's just the z component, and specifically this is at z naught, so x comma y comma z naught. And so I have, minus the integral over R of R of x comma y comma z naught dx dy. So what happens when you, let me call this 1, let me call this 2. What happens when we add 1 and 2? We have the double integral of R of x comma y z naught plus delta z minus R of x comma y z naught, right? dx dy. And that's over the region R. So what happens, what are we looking at there? Volume of what, though? I mean, this is, we can rewrite this, right? It's a little sneaky, but here's how to rewrite it. That's the integral from z naught to z naught plus delta z, right? And then I can do my double integral over R of partial R partial z, all right, of dz dx dy. Do you see how that is? So like the antiderivative in the z integral is just R. R evaluated at the upper bound and the lower bound is exactly what I have before I wrote the triple integral. So Sam's right, it is a triple integral. And it's also the triple integral. So like just to clarify here, that's exactly the triple integral over the volume in question here of partial R partial z dv. So put this all together, what do you got? The flux through of F, right, which is equal to what? The flux through caps plus the flux through the side, curved side, right? That gives us, in particular, F dot ds over the boundary of the solid is equal to the triple integral over the solid of partial p partial x plus partial q partial y plus partial r partial z, which of course is the divergence. Now, this proof, of course, is what? It's just for this really special solid, which has horizontal, flat caps, a flat cap and a flat base. And admittedly, I'm also kind of assuming that it's stubby enough so that there's not anything too interesting happening on the side. I mean, this could be nuanced more to capture like variations in z in the I mean, really, if I did this proof carefully, it would pick up on variations in the number of field lines going through a particular z slice. All right, I've just been a little bit sloppy this morning. Any questions? Now there is a proof in the notes I give a proof in the notes for the case that, I give an explicit, gory, fundamental theorem of calculus-based proof for this on the case of a solid region like this later in the notes. Like for a cube, I explicitly work out the divergence theorem for that shape. All right? Like there's a gory step-by-step proof of that in the notes. If you don't fully believe what I'm doing at the moment, if it's too sketchy, right? You can prove it for that. Okay, so if you can prove it for that, then of course, like, are we going to apply the divergence theorem just to cubes and to like cylinders? Well, no, like we're going to apply the divergence theorem to much more exotic shapes, right? So suppose you're dealing with some sort of three-dimensional blob and you want to apply the divergence theorem. Can you still do it? Well, here's the thing, is you can take any three-dimensional blob and you can break it into what? You can break it into a bunch of cubes or a bunch of, what would you call it here? Or cylinders, if you like, I suppose. I'm not very good at drawing this. I'm just trying to illustrate the idea. All right. But if you can imagine that, it's not hard to imagine that you could build any kind of three-dimensional thing from a sum of a bunch of little cubes put together, right? What happens as you apply the divergence theorem to a union of such cubes that fill out a volume? Like in particular, what's the deal with two cubes like here and here? They don't have to be cubes either, right? They could be sort of like oblong. What's the situation with the flux that you calculate? If I take the sum over cubes, what happened? Cubes of the flux of F. And let me just call them E sub j for the sake of discussion. Actually, the boundary. Let me call E sub j the cube. So the boundary of E sub j would be the flux, and that would be equal to the sum, right, over the cubes of the triple integral of the divergence of F, right? Because I can apply our cube divergence theorem for each cube, right? I'm thinking the union of all these cubes. So like, first of all, this is literally the integral, triple integral over the union of the cubes, right? Because that's how integration works. The sum of the integrals is the integral over the union of the regions which you're going for, right? If I have an integral over a union, I can break it up into a sum over the integrals of the sets which are taken as union. So this side just gives me that, right? But on the other side, something interesting happens. What happens when you add up those flux integrals? I mean, yes, you would get the sum over the boundaries, but we can just write it as, the integral of f dot ds over the boundary of, well, let's just say the exterior, boundary of all the cubes union. See, because what happens is on any interior face, right, so the orientation's always like this, guys, right? Outward facing. So this face right here, from the blue one, I go like that, right? But from the right one, the outward directed normal, well, it's up here like that, it's down there like that, it's over here like that, if you can imagine that. But at the place where they meet, it's the other way. So what's going on is every interior face where two such cubes meet, sorry, it's hard to draw everything and not make something looks like it's going from somewhere it's not. I tried. So at any interior face, you have the normal from one cube going one way. You've got the normal from the other cube going the other way, but it's the same point set. It's just the same point set with opposite orientation. So when you add the flux integral from the side one cube to the other side cube, those cancel. And all that you're left with is every exterior face. You should have a strong sense of deja vu. This is the third time I've made this argument, but in very different contexts, right? First for like an area integral, then for a surface integral, now for this volume integral in some sense. I mean, well, anyway. So yes. So this is the divergence theorem. So it's true for more interesting shapes. Any questions? What if you had a hole? So this is all for a simple solid, right? Like what would happen if your solid had a hole in it? How would that go? So I don't know how to illustrate that. Suppose you have like that. So here's a hole. So I'll draw it two-dimensionally because it's easier for me to draw for a second. So the definition for this would be something like we have ds like that, but then for an interior surface we define ds to be like that. So if this is E, so the boundary of E, it has outward pointing ds for outside boundaries, and it has inward pointing ds for inward boundaries. Now you will ask me, and of course, what's the real rule? The real rule is that whichever way the normal is pointing on the boundary of the solid, the normal is not pointing into the solid itself, local to the surface which it's bounding. See, because Sam will soon ask me, what about an island inside the hole? What about there? Right? So, since I know this answer, I can read the room. I know what's coming. So what if we had this? What if your solid was this? So here's, so you'd have ds out here. The ds would be here like that. And then ds would be like this here. If you were so foolish as to try to integrate over such a region, that would be how I would define the orientation of the boundary. It's always going outside of the shape that we're talking about. So E I have in mind here is this. That's a hole. All right. And here, E was just here. So let me draw another picture. You can take a sphere with a hole in it, kind of take it like this, and imagine separating it. All right? So basically I'm just taking the hole and I'm separating it. Let me draw the hole in a different color. So the interior. And what would happen if I do that, right? If I take this like sphere with a hole in it, like a gumball, right? Without the gum. You guys have gumballs before, right? Nobody? I should have brought gumballs today. Like a jawbreaker. You know, the interior part with the substandard candy that you get to? Once you're past the really good stuff, you know what I'm talking about. Or you like the inner side? You like the inner part more? No? Okay. Anyway, the point is that once we chop it, the upper half and the lower half, these are both what are called simple solids. What's a simple solid? A simple solid is a solid region which does not have a hole. Okay? Basically, I cut the hole in half, and in so doing, I make the hole into an exterior boundary of the half. It's no longer a hole when I look at the cut pieces. So, and the simple solid, we've already derived the divergence theorem for simple solids, right? So if I call this one H plus, and if I call this one H minus, I can take the integral of a vector field, right? The flux along H plus the integral along the flux along H minus, right? And that's actually going to be equal to the integral along the boundary of the sphere, right? On the other hand, this is the triple integral of the divergence, you know, along, let's say, E minus, E plus, and then plus the integral of the divergence along E minus, right? And then, of course, that's just the triple integral of the divergence over the whole thing. Why the only interesting aspect of the most interesting aspect of this calculation is this right here. Why is it that the integral, so this is the boundary of E plus, this is the boundary of E minus. What's the interesting aspect here? I mean, it's not the same flux calculation, technically speaking. There's two extra pieces, one in each part of the integrals being summed, right? Like on the E plus part, you've got this band right here, right? This right? And it's got its normal pointing that way, right? And this is pointing that way as well. But on the flip side, on the lower part, like that's an extra piece that's not in the boundary. Well, the aw man, sorry. I'll do better. So sorry. And then on the base, right, here you've got this band, right? And there you've got your normal. So first of all, inside here you've got ds like that, right? And here you've got ds like that, right? So you notice that, again, it's an interior, it's like a crosscut we talked about before. The normal from the upper part's pointing down, the normal from the bottom part's pointing up. It's the same area that's being sliced. So when you add those pieces of these flux integrals, they cancel. And all that's left is the top of the hole and the bottom of the hole with the orientation pointing inward, as we demanded in the definition of the boundary of E. And the thing is, if you can do it for one hole, you can do it for n of them. So this argument can be extended to more. Okay? So, now that I've got these proofs out of my system, let's work some examples unless there's a question about something in particular. So now we've got options, right? We can see, this is the thing. Now, so I graded the quizzes, and well, okay, so we have work to do. I mean, you have work to do. Yeah. I mean, I can show you examples, but you know, you got to think more about them. And I know we're just getting started, and there were CFAs here distracting us, and Benjamin was the destroyer of worlds last week as well. So there's all that. But I'm hoping that you can get past where you were and understand how to do some of these calculations, because they do matter, and you do need to learn them. Okay, so let's do an example. The larger point here now, though, is we have the Stokes theorem and the divergence theorem that we can both wield to solve examples. So, you know, as we're going through examples for the rest of this week, we always have to ask ourselves the question, could we use the Stokes theorem or the divergence theorem to help us out, all right? It may or may not be the case. Let's see here. Let's look at this half cylinder. All right, so this would be x squared plus z squared equals to 4. And let's let this thing range from y equals 0 all the way out here to y equals 10. All right, so that's my surface. That's my surface. I'm going to find the flux of f equal to x squared y z plus 2. Oh, that's too simple. My bad. X squared y z 3 through S, oriented in positive z direction. So first of all, I will tell you, I don't think that the divergence theorem really has any bearing on this whatsoever. I don't think the Stokes theorem is even any helpful here, okay? So let's just start with that. So how do we do it? What's the first order of business? We need to figure out what ds is, that's right. So, I mean, I can picture it, something like this, right? Yay. So let me suggest for this, we should think about x equals to 2 cosine beta, y equals to, not y, but z, right, is 2 sine beta, and y is equal to y. All right? So if you do this, if you want to picture it, it looks something like this. If this is the z-axis and this is the x-axis, then this angle here is beta, right? That would be a picture, kind of. Straight down the barrel of the y-axis, if I did it right. Maybe I didn't. Well, if I do this, the y is pointing straight into the board. Just, if I write it like this, the y is pointing straight into the board. If you want me to make y point out of the board, then I have to put x over here, right? And then the beta would look like this. See, the reason, where does beta start? I'll do it that way. So x crossed into y gives me z. That's how I know where y is into or out of the board, sorry. It doesn't really matter which picture you draw, because y is kind of not the point here. let me just point out that the surface in my two-dimensional picture looks like this, all right? That's essentially this kind of curve, all right? So my main point for drawing this is to try to explain to you, we want beta to range from what to what? You guys tell me, what should I make beta range from? 0 less than or equal to beta, less than or equal to pi. And y? Well, y goes from 0 to 10. All right. Cool. Now we have, pretty much fixed our parameterization. Now we need to find the ds, right? So let's do that. So my parameterization, and you could use x, you could use r. I'll keep using x. I've been using x for the most part. Let me just think about this for a second. I just, guys, I don't usually think about it. What I usually do here is I just write something down. So I'm just going to go beta y. If it goes badly, after I calculate the cross product of the partial velocities, if it points in the wrong direction, I just switch the order of the parameters. No big deal. But you got to watch out for it. So this is, in particular, 2 cos beta, 2 sine beta, y. Right? And, okay, so my partial velocities, minus 2 sine beta, 2 cos beta, 0, and partial x, partial y, 0, 0, 1. Take the cross product of these to get the normal in the beta y coordinate system, and that gives me, let's see here, 2 cos beta, 2 sine beta, 0. And you can, whoa. Oh, come on. Seriously? What's wrong with me? Well, many things, but do you believe this? Do you guys believe this? Oh, it's so much worse than that.
The y is in the z spot.
Thank you. So somebody saw that like 2 minutes ago and didn't tell me, you monster. All right. You're like, I'm not sure I'm right. Just, no one cares. If you say something that's wrong, but it's wrong, and then that's fine. We move on. If you say something that's right, and you weren't sure about it, then I didn't waste 2 minutes. That's much better. So just say something when you see something. Someone here saw that. Come on. I don't believe everyone didn't see that. Goodness gracious. So partial x, partial beta, minus 2 sine beta, 0, 2 cos beta. And this is 0, 1, 0. All right. And so what goes on here is that puts a 0 here, and that puts a 2 sine beta here, I believe. Is that good? I mean, let me ask the question. Does that point up? Is this the ds pictured? Do I need to stick with beta first, then y second? Or do I need to switch the order of my parameters? Am I oriented correctly? What do you guys know about sine beta? What does sine beta look like from 0 to pi? Right? Here's pi. Sine beta is positive. Yay! So we got lucky. 50-50, right? Yep.
I got the negative of that.
Aw, man. I guess I should actually calculate it. I was guessing. This is what you get for guessing, right? See here. Oh yeah, I better look at the right vectors, right? That would be good. That would be a good start. Oh yeah, you guys are right. It's minus. So they're both minus. All right. Well, so bad news. Bad news. That's opposite the orientation we want, right? So what do we do? Right, no problem. So, okay. So use x of y beta instead. And then the normal in the y beta coordinate system is simply 2 cos beta, 0, 2 sine beta. So see, it doesn't really matter which order you choose the parameters as long as you check. Once you're done with the calculation of the partial velocities and their cross product, and make sure that it actually points in the direction that you need. And also, it's helpful to actually calculate the cross product as opposed to just guessing them. You know, point of order. But that's good. That's what I got you guys for. Let's see here. Anyway, I need to lose more points. I've got too many of your points right now. So you guys should get some points back from me, you know? Let's see here. So then what? So then, yeah, we found the bounds. So now we just need to do the calculation. So the flux of F through the cylinder, we do integral from 0 to 10, integral from 0 to pi. My F of x of y beta dotted with the normal of y beta, right? D beta dy. So specifically that is, what is F? So F of x, so we're putting x equal to 2 cos beta, so we've got ourselves a 4 cosine squared beta. Yz, what's yz? Yz is y times 2, so it's 2y sine beta. And then the z component's easier, it's 3. And we're taking the dot product with 2 cos beta, 0, 2 sine beta, d beta, dy. All right, so we're up against the integral from 0 to 10, integral from 0 to pi of apparently 8 cosine cubed beta. Hey, that dot, I love 0, 0, and then plus 6 sine beta, d beta dy. That's interesting. So the y integral is trivial. In other words, I can just multiply by 10, and then I'm up against the integral of like 8 times 1 minus sine squared beta, cos beta, d beta, 0 to pi, you know, plus the integral from 0 to pi of sine beta d beta times 6. This integral is 2. This integral is 8 times u minus u cubed over 3, evaluated from 0 to 0. That's funny. Look at that. If you make a u equals sign substitution there, what happens? That's funny. U equals sine beta. What happens to the bounds? So beta equal to 0, sine of 0, 0. Beta equal to pi, sine of pi, 0. That integrates to 0. Woohoo! This integrates to 2. 2 times 6, 12, 120. All right, so why didn't I use the divergence theorem or the Stokes theorem here? A couple reasons. Number one, why didn't I use Stokes theorem? Well, there's no curl in this question, all right? No curl probably means no Stokes theorem, usually. That's not a general truth. Why didn't I use divergence theorem? This is not the boundary of a simple solid, right? It's half of a half, it's the top boundary of a half cylinder. For the divergence theorem to be a useful tool here, I'd probably need to look at something like a half cylinder. You know, if I had a half cylinder missing its base, then the divergence theorem could still be useful. We'll look at examples like that. Kind of like on the quiz where I gave you partial information and you can kind of piece it together. We can do problems like that. But anyway, that's probably it for today. I hope that helps you. Oh, I guess the other thing I should say, what if I wanted to do the integral over the same thing, but like of z squared ds? How would that go? What would ds be here? What's the magnitude of the normal? It's 2, right? So this would literally just be the integral over s of, well, this z squared would be 9, ds would be 2 d beta dy, and so the answer would be 18 times pi times 10. It would be 180 pi. Wait a minute. Yeah, 180 pi. Anyway, yeah. I'm just saying, once we've set up the flux integral, we can set up the scalar surface integral by just taking magnitude and integrating. So.